This video is going to be an introduction to our next unit, which is thermodynamics. So thermodynamics is the study of energy transformations. And we'll be focusing specifically on energy transformations within chemical reactions. So when I say energy transformations, that can mean either energy moving from one place to another, or energy changing from one kind to another, or a combination of the two, changing from one kind to another as it moves from one place to another. So there are two main categories of energy, and there are kind of subtypes within those categories, but two main kinds of energy in the universe that are known as heat and work. So chemical reactions transfer energy as heat. So that is where we're going to be focused, is really on a discussion of heat and heat flow. And we won't really be discussing work. Work is a type of energy transfer that usually involves something moving. It's kind of the easiest way to think about it. For instance, anything that moves due to gravity, like if you drop something and it falls, that is work being done. The gravity is doing work on that object. Energy transfer in chemical reactions is usually pretty exclusively heat type energy. You know that if you get near a fire, you feel the warmth. If you touch something on fire, you will be burned. And that is due to the heat energy that is being released by that reaction. So we'll be talking a lot about how and why heat transfer happens in different situations. And we're starting kind of simple and working our way up to chemical reactions pretty shortly. So the first thing to think about with heat is what happens when substances of different temperatures come together. For instance, putting a glass of hot coffee, mug of hot coffee on a desk and just leaving it there. You know intuitively that it will cool off until it reaches room temperature, that your hot coffee is not going to be hot very long if it's not in an insulated container, and even if it is, it will cool off eventually. So that when substances of different temperatures come into contact, heat transfer occurs. We are transferring energy as heat is why the temperatures change. So when substances of different temperatures come into contact, energy is transferred as heat from the hotter substance to the colder substance, until the temperatures are the same. And we refer to this process as reaching thermal equilibrium, that when all the temperatures are equivalent, once your hot coffee has cooled down and it's the same temperature as the surrounding air in the room, we say that it has reached thermal equilibrium. So thermal equilibrium is when all temperatures, or when all substances are the same temperature. So we'll be talking a lot about temperature and temperature changes because it's intrinsically related to this idea of heat transfer, that when heat is transferred, temperature change is one of the most common ways that we detect that. So we should be aware of what temperature really is. So when we measure the temperature of something, when we stick a thermometer in it and say it's 86 degrees or whatever the case may be, what we are really measuring is the average kinetic energy of the particles. And kinetic energy is related to how fast the particles are moving, that the faster your atoms and molecules are moving around at the molecular level, the higher their kinetic energy. And we measure that as a higher temperature. So something that is hotter, as we usually think about it, really just means that those particles are moving around a lot faster at the molecular level. So kinetic energy is often described as the energy of motion. Something that's moving faster has a higher kinetic energy. In general. Mass is also part of the kinetic energy equation, but if you have two things of equal mass, the one that is moving faster has higher kinetic energy. So it's important to keep in mind how temperature and heat and kinetic energy are all related. These three terms tend to get used interchangeably, but they're not interchangeable at all. They have different meanings. So heat is the transfer process of energy. Heat is how energy moves from one substance to another. Kinetic energy is the intrinsic energy within a substance or within a particle related to how fast it's moving. Heat transfer can change the kinetic energy of a substance, and we measure that as a change in temperature. So temperature is a measurement. Kinetic energy is the amount of energy that, or an amount of energy that a particle or a substance contains. Heat is how that energy moves from one substance to another. So to kind of summarize this in a sentence, heat flow or heat transfer can change the kinetic energy of a substance. And we measure that as a change in temperature. So also related to temperature, we have a few different temperature units or temperature scales that we use in science. In the US, in weather and common everyday life, we use the Fahrenheit scale, but the Fahrenheit scale is not used in science at all. The two scales that we use in science are Celsius and Kelvin, and we will use both of those now. You're probably more used to Celsius, but they're both important. And in thermodynamics, Kelvin becomes much more important and much more commonly used. So we have two different temperature scales. That we use in science. So we've got Celsius, which is abbreviated degrees C. degrees Celsius. The Celsius scale, when it was created, is defined around water. That science decided that it would be convenient to have a temperature scale where everything was based around the temperatures at which water is a liquid, because that is how things tend to exist on Earth. Those are the most common temperatures that we encounter. So in the Celsius scale, 0 degrees Celsius is where water freezes and melts. It's the freezing point of water. And 100 degrees Celsius is where water boils and condenses. So this is the definition of this scale, is how Celsius is defined. As 0 degrees Celsius is the freezing point of water, 100 degrees Celsius is the boiling point of water. So most commonly we deal with temperatures between 0 and 100, which is convenient. They're nice numbers to work with. But the scale is still fairly arbitrary. So convenient numbers for us to work with, kind of random, like why water? Yeah, water's everywhere, but it doesn't actually have any significance in a physical chemistry standpoint. So the other scale that we use is known as the Kelvin scale, which is just abbreviated capital K. There's no degree. The unit is not the degree. The unit is the Kelvin. So in the Kelvin scale, which is also sometimes referred to as absolute temperature, this is the only temperature scale where the measurement of the temperature is directly related to molecular motion, is actually directly related to kinetic energy at the molecular level, which is why this is going to be really important for us when we're talking about thermodynamics. So this is the only scale where temperature is directly related to kinetic energy. Zero Kelvin is also known as absolute zero. Is where particles have zero kinetic energy, where all molecular motion stops. So at absolute zero, literally nothing is moving. All particles have zero kinetic energy. Everything stops completely. So in the Kelvin scale, we're really directly measuring how much kinetic energy does this have, in different units, of course. But the temperature in the Kelvin scale is directly related to the kinetic energy. Zero actually means something here. 0 degrees Celsius is actually pretty warm in the grand scheme of the universe. 0 Kelvin is literally as cold as anything can possibly be. And we actually can't achieve absolute zero. We can't get substances to absolute zero in a lab, or at least we can't know about it, because to take a measurement, something has to move. Even if you are taking a measurement with a digital probe or some kind of computer, photons have to move, energy has to move, electrons has to move in order for that measurement to be registered, for that information to move. Something at the molecular level is moving. So Absolute zero is kind of a theoretical thing that we can't actually achieve. Even in the deepest depths of space, you're not really close to absolute zero. Your temperature is still a few Kelvin, even in the middle of nowhere, away from any stars. So these are ideas that we're going to be talking about quite a bit as we move forward using the Kelvin scale for temperature measurements and calculations to help us really relate energy transfer to temperature and how heat transfer can affect temperature.